can start anyway.
Okay.
I'm going to stay here until we make sure that it works.
Okay, great. Well,
I have to go up and down the line.
Yeah, I'm extremely pleased to introduce our guest speaker today. She comes from the University of Michigan, Dr. Ella Atkins. And she has quite a storied past, and she's a professor in the Aerospace Engineering Department, where she directs the Autonomous Aerospace Systems Lab and is also the Associate Director of the Robotics Institute. Dr. Atkins holds a BS and MS in Aeronautics and Astronautics from MIT, and an MS and a PhD in Computer Science from the University of Michigan. She is an AIAA Fellow, yay, and she is a small public airport owner and operator, a private pilot, and a UAS pilot as well. She's also busy as the editor-in-chief of the AIAA Journal for Aerospace Information Sciences. So we're very pleased, and we hope that we get our information sciences working here for you in the very soon. So
sounds good.
Let's welcome Dr. Ella Atkins.
So obviously I'm going to talk for a little while without slides, and I know that'll be distracting, but I'm going to start with a survey that I have been asking people for about 25 years. So a lot of what I do deals with autonomy and safety for aircraft, both manned and unmanned. And so here's the question, and it goes back a long time. Suppose a brand new shiny commercial transport aircraft was at gate, I don't know, D7 at Fort Lauderdale. That's kind of where I came into. And it had no cockpit. Instead, there was a bank of computers with sensors. Now, it had been certified by the FAA, and whatever your favorite airline is, they have just rolled it out, and they've flown it before. It's not like it's the first flight. And you've purchased a ticket, and you're supposed to get on board. Will you do it or not? Will you go back and demand a refund? So, this is a fully autonomous commercial transport aircraft, no human pilot on board, no remote pilot supervising it, all software, all autonomy. How many of you would get on board, fasten your seatbelt, and have a good time? Okay, maybe you wouldn't have a good time, but you get on board and fasten your seatbelt. How many of you would say, no way, I demand a refund, you'll be standing in line at the ticket counter? Okay, so a lot of you didn't actually raise your hands. I think there were slightly more no ways than there were definitely yes, I'll have a good time. For those of you in the middle that didn't raise your hand, assuming you're actually listening as opposed to being like, I'm just not going to participate, what would sway you? Anybody willing to speak up and say, okay, yeah.
Past history of their performance.
Okay, so now let's add some past history. Let's say that this brand new shiny plane, let's call it a 797 plus. We won't use the word max. Let's say that it had so many spectacular success stories in the media, right? Because the average passenger is not going to be at an engineering school where they've actually looked at technical papers or reports describing the performance. All they're going to know is that the media has put shiny pictures of an airplane with no pilot on various websites and social media and newspapers. That's all you're going to get. Does that help? Okay, so now let's say that it has a lot of publicity that has shown you that it works. How many of you will now get on? This is about the same number as raised their hand before. Right, so what about ATC? So this is a future that's very consistent with urban air mobility, where data link provides precise position information based on GPS. ADS-B provides traffic information to the autonomy or the next generation system beyond ADS-B, because you could raise your hand and say in the next generation airspace, there's too much traffic and ADS-B won't work, which is true, by the way. But let's ignore that for now and assume that there is a detect and avoid system on board. So there is definitely a switch in mindset that needs to happen, because I don't think a lot more people are going to raise their hands even though they're now hearing that ADS-B and data link are present. And the reason for that is because there's just kind of a psychological fear of sitting on a commercial transport airplane, trusting your life to those computers up front. So it's interesting because if I go back about 25 years, which is the first time I asked this question, it's a little bit higher percentage of this audience that said yes than that said yes 25 years ago. But it's not all that different. Meanwhile, if you look at cars, I'm going to ask you the companion question. Let's say that you call Uber. Forget what happened in Arizona. Let's say you called Uber and they show up at your house with some reputable name, Toyota, Ford, pick your favorite manufacturer that you trust, and there's no human driver, and there's no steering wheel, and there's no brake, and they say, climb in. We'll take you from this gate at Fort Lauderdale where you have denied being transported on this autonomous aircraft. And we have now said, okay, I need to come back to Miami, which is what, a 45-minute drive, freeway speeds, autonomous car. How many of you would get in that car? So this is about the same group. So I think, how many of you would not get in that car? Okay. So this is something to think about. In general, it's been my experience. Now I live in Michigan, it's auto central, and people think about autonomous vehicles only as cars, which annoys me because I like the planes better. And a vehicle can be airborne as well as on the road, or submerged, or on the surface of the water, pick many other forms. And in general, what I've seen is that people are more willing to get in a car that's autonomous than a plane. And I think the reason for that is that, A, we imagine that the autonomous vehicles around us are being driven by teenagers and old people, and that we're better protected having autonomous systems preventing them from doing bad things. Right? Whereas in a plane, we're assuming well-trained cockpit crews are flying the plane. Right now, is this necessarily going to be the case moving forward? Well, as long as we have exactly the same technology right now with 2 human pilots up front that have an illustrious history of coming through Cessna training all the way up to commercial airplane flight, then yes, it's going to be like it is now. The problem is now we have this thing called urban air mobility where we think air taxi, and we have unmanned aircraft systems. We're not going to have enough well-qualified pilots to fly these vehicles. No way, no how. So we're going to have to go to simplified vehicle operations, which I have a couple of slides on. We'll get to them now that they work. And what that means is that we're going to have pilots that have roughly the same amount of training as an Uber driver. Right? So now if you rethink how much it makes sense to get in a modern urban air mobility air taxi and look up front and there's a 20-year-old flying you around, and think, is this safer or less safe than taking that 20-year-old out, adding another passenger, and having triply redundant, certified, long history of testing autonomy? I don't think the answer is so clear. So that's the thought problem that you usually can stall until things work, like this presentation. So now let's see how the slides are feeling. Yay, it's there. That's exciting. Pay no attention to the label. This is the Miami presentation. Yay, it's there. That's exciting. All right, so I'm going to talk today about taking data and making decisions for safe flight, but an implicit part of this presentation is that it's increasingly autonomous flight. If we look at the unmanned and the urban air mobility applications, that's what drives it. So this slide is intended just to give you the proper vision of what we're going to have in the future. We're going to continue to have the jets that fly out of Miami and Fort Lauderdale. No question about it. That's how we get around right now when we fly. They're not going anywhere. We also want to still support general aviation. You know, the banner tows, the Cessnas, all of the things that you see around here that are just little planes flying up whenever they can punch a hole in the sky. We expect there to be at least 10 to 100 times more unmanned aircraft operations per day than manned aircraft operations in the next 5 years. Right? Think about that. Right? Because every time somebody goes out with a drone and delivers a package or takes some camera data, they're actually an operation in some form of airspace. Right now they're supposed to stay low unless they're military. But that's not going to last, especially when we get to that last type of operation, urban air mobility, or UAM, which is the air taxi. That pushes the notion of getting up into higher altitude airspace, because the last thing a passenger in a maneuvering multi-motor contraption that's flying them from point to point is going to want to do is to skirt below the rooftops, right? Which is what you're going to end up as if you're flying in an urban area. You know, one of my students made a map of Manhattan, and he's been looking at rooftops. You'll see why in a minute. But if you cut off the airspace at 400 feet above the ground, you cut off the roofs of a lot of buildings. So you are in the urban canyon. Now the FAA would say, it's 400 feet above the tallest building in the area, right? But now look at New York, look at Manhattan. If you go 400 feet above the tallest building in Manhattan, you are right in the middle of the airspace that serves the approaches and departures for Newark, for Kennedy, and for LaGuardia, right? You can't be there. We don't want drones there, because then they're going to hit a bunch of the approaching and departing traffic. So what that means is that we don't have a nice, clean segregation of airspace for the little drones and the manned aircraft. Longer term, we're going to have to mix them all together. So that brings in the concept of advanced aerial mobility, right? Which means we have to improve the technology across all sectors of aviation to allow them to coexist. We are not going to have, 20 years from now, a standard which says the Piper Cub with no radio can punch a hole in the sky without any equipage that allows the unmanned aircraft to detect it. That's not going to happen. And that doesn't mean that I am anti-freedom of flight, which some groups would say. I'm a pilot. I have a grass strip. General aviation is the only traffic that comes in and out of there. But it just doesn't make sense in the 21st century, where general aviation pilots put tablets with Velcro on their control columns and use their phones all the time to get flight plan approval, to then draw a line and say, these people don't have to have a radio or any sort of other equipment other than ADS-B, which is going to break when you mix a lot of traffic in a dense airspace. So how do we get there? Well, first of all, you try to figure out how to get there. What functions do you need? What pathways do you need to follow? And then what can go wrong? A lot of my research, which is focused on safety, not so popular as a cool new technology, because safety doesn't sell. Safety is just something you want, because you don't actually want to break stuff and have people die. You have to investigate that. So I'm going to then talk about 2 research projects that my group has been working on for a while. The first one is looking at airspace geofencing that is more or less for the low altitude small UAS. It's an alternate way of looking at airspace when most of your missions are not long distance point to point, where you just track that trajectory over time. The second topic is going to be autonomy for contingency management. So when things go wrong, what do? If you're an aircraft that is not a military aircraft on a mission where you have to trade off safety with getting the mission done, and sometimes you don't care if the plane crashes, you still want to do the mission. Not that. This is civil or commercial aviation with a peaceful purpose. Whether you have a package flying it over a city or a person flying it over anywhere, your first priority when something goes wrong is to get down on the ground safely without crashing. So that's a lot of what my research has been looking at over the past few years, because that's pretty hard. Not day to day, but when things go wrong. So these are the functions that advanced aerial mobility, or AAM, really have to do. First of all, you have to have situational awareness. The obvious thing is you have to bring the sensor data that's on the aircraft into the software and figure out what to do with it. estimate your state. The new thing that I'm going to talk about in the second part of my presentation is, if you have data link, you also have access to the cloud. This is that proverbial cloud of data where you can get anything you want that's available on that network. The second step is that you have to be able to analyze whatever your state and your data say and make decisions. You have to be able to warn or inform other vehicles in the area, people that are either in the aircraft or external at a control station somewhere very remote, what's going on. You have to be able to act once you've made decisions in an appropriate way. Limit when either autonomy or humans make some kind of decision error. So this requires an independent module to watch and see what's going on. The classic example in aviation and many other industries right now is, let's say you have machine learning active right there on an aircraft. Well, we right now don't really have a full understanding of what all the stimuli going into that machine learning module are going to do to its model of the world. So when we send new data in, it's not 100% guaranteed to return a correct or even safe output. So if we wrap that machine learning with kind of a watchdog that says, is this output something that could be correct? It's not, is it optimal? It's, could it possibly be correct? And in the vein of the 737 MAX, which pitched down and crashed 2 different times and has been a big, big nightmare for Boeing, and people are afraid, and airlines are now without flights going to many places that flew those routes with that plane. That watchdog would have said it never makes sense to pitch an aircraft toward the ground at such a low altitude. Right? It doesn't matter what your airspeed or your angle of attack says. That is just a basic physics of flight, situational awareness problem that says this software must be flawed. Right? And that wasn't even machine learning. So as we become increasingly autonomous in our operations, it is important to wrap decision modules with a capability that monitors and limits their performance to something that could make sense. And then we have to put everything together. That's the integration box. So when we think of advanced aerial mobility, there's 2 paths to getting the Jetson-like, fully autonomous, direct flights with air taxis, with unmanned aircraft carrying your packages wherever you want them, mixing with all the commercial transports. One is called the piloted path, where we start with state-of-the-art right now and incrementally make it better. That means the vision should be helicopters and commercial transport, and we're adding features, eventually taking the pilots off and then getting toward autonomy that way. The one on the bottom, which we're also engaged in right now, is starting with the unmanned aircraft. You know, all those people like Amazon and Google that are out there saying, we can do it today, we can take packages to your backyard. Right? They have a lot of technology on their vehicles that is in parallel, not assuming that there's a human pilot on board, but is assuming that there's a remote pilot with a lot of sensor data. So those 2 paths ultimately converge when we have full autonomy. This is showing the piloted aircraft path, where we transition to something called simplified vehicle operations, or SVO. In that model, the pilot doesn't have to have as much training, so they become the Uber pilot. Right? And the Uber pilot, because of the scale of the number of pilots that they would need, will not be well trained. But if the autonomy is caught up with them, they don't need to be well trained, because they're basically serving the monitoring function and saying, is this ridiculous or not? The next step is to move them off board, get that extra person on, get them paying to actually go from point to point, as opposed to putting a human pilot on board, which takes one of the seats. And then you have a problem that involves making sure you have a robust data link and that the people sitting at the control stations have all the data they need. And then finally, you can move to the autonomy. One of the things that really is fascinating in this picture, do any of you do human factors? Interested in that kind of thing? Well, so this would be the first kind of operation that had human passengers, but neither had a human pilot nor flight attendant. Right, so here you are flying. Maybe it's turbulent. Maybe there's lightning. Maybe somebody gets sick or has a heart attack, or a kid just decides they don't want to fasten their seatbelt anymore. Right? What does the autonomy do? right? This is actually a question that's not being very heavily studied yet, and I don't study it either because it would scare me to death to think that my autonomous plane had like a couple of kids fighting with each other, deciding to, you know, hurl their bodies against the side of the mini helicopter, right? Because autonomy can't do a lot about that, right? So there actually are some pretty interesting questions in psychology and interaction which deal with how do you manage passengers when you have no idea what the personalities or psychological or physical state of those passengers are. So that's not here on these slides because from the autonomy and aerospace perspective, we assume that they're sitting there with their centers of gravity in the right place and their seatbelts on, right? And that's a desirable thing. So this shows the path, which is very similar to the piloted path from the unmanned aircraft to the end state. Here I'm showing one of the more sophisticated fixed-wing aircraft. It's one of the NASA vehicles. The reason I show that instead of a quadrotor is that the technology on that vehicle is a lot closer to what you would need for full autonomy than on a little toy quadrotor. So there's a lot of things that can go wrong, right? And one of the reasons to show this slide, I'm not going to leave it up here very long, but one of the reasons to show it is you have to deal with these before you take the people out, right? Seriously, you have to deal with all of them. If you have decided to conveniently assume that one of these is never going to be a problem, then you're going to have accidents. These are hard problems. Each one of them is research. Each one of them is development. Each one of them is making sure that as a researcher, you state your assumptions. And then by doing that, it alerts the rest of the research community as to what they have to relax in terms of assumptions before the problem will actually be solved, right? This is one of the things that the .com world is extremely bad at. Right? They don't ever come in saying to the investors, you know, this is really shiny and cool technology, but I have assumed these 10 things that will make it never work. Right? They wouldn't get the big bucks to keep going. But in academia, that's actually one of our big responsibilities, is to make sure that whenever we write about something that we say, here are all of the assumptions that we've made, and then in our future work and conclusions sections, we talk about our results in the context of what's next. So please don't forget that. And I know there's a lot of things here and I could go through them, but then I would get distracted and it would take 10 minutes, so I'm going to go on. So now I'm going to talk about geofencing. This is a picture of UAS Traffic Management, or UTM. This is a concept that NASA Ames primarily introduced about 4 or 5 years ago, and it has had a lot of input from the community, ranging from FAA to a lot of the drone operators that want to deliver packages and take data in cities. And the concept here is that we already have classifications of controlled airspace that support commercial aircraft and general aviation. And if we look at a lot of the small drones, they're going to be at low altitude under 400 feet. Now, this is not my vision of that advanced aerial mobility that will last a long time, but this is the going in, how do we get these things up in the sky being operated today without causing a bunch of manned aircraft to be hit? So then the yellow, the UTM operations, is the under 400 feet mark away from cities and airports that would allow drones to operate now. And it is basically where drones operate now. So this is a picture of the southern tip of Manhattan. So why would you have a strange shaped airspace volume to operate in? Well, this is one of the motivations for that. If you're in a densely populated area with New Jersey to the left, Manhattan above you, and I guess that's, what is that? Brooklyn? Yeah, thank you. I was thinking Queens, and I'm like, no, that's not Queens. Okay, Brooklyn to the right. You don't want these little drones flying over people that are on the street, walking their dogs in the park. You don't want them hitting the buildings and so on. So if you wanted a drone to be out doing something like sightseeing, you probably would want it to stay over the Hudson River. Now, you could raise your hand and say, wait, isn't that where all the helicopters and all the Cessnas are asked to fly? The answer is yes. Well, the Cessnas aren't supposed to fly below 500 feet. So again, I would say you're okay if you stay below 400 feet. That's fine. But look at the shape. That's not a very nice shape. So you could say, well, we don't need to do that. We'll just draw a rectangle. Well, it would be a very small rectangle because of the Statue of Liberty and Ellis Island and Governor Island, because you don't want to fly over them either. right? So what you really want with a geofence is the ability to keep an aircraft within a concave polygon boundary with cutouts. So what we looked at with geofencing, instead of putting a tube around each vehicle and saying, okay, we're going to track it as it flies across the sky, a lot of the small UAS missions aren't like that. They will stay in a common area, and we need to tell them what their limits are. So this whole research project was looking at an alternate model of airspace where we used geofencing to deconflict the airspace, but then whoever was in each boundary just has to stay in there. So a lot of people do research like with swarms. However, are we going to deconflict two swarms from each other when they don't use the same cooperative control algorithm? Right? That is the problem that no one has really solved. In fact, they haven't even addressed it yet, because swarms usually have like vehicles that communicate with a known algorithm. Well, with a geofence like this, you could actually put a swarm of 1,000 vehicles in there. And as long as that airspace was off limits to everyone else, that swarm can do whatever cooperative control algorithm it wants. Right? So these are kind of motivators to have a whole research study of concave polygons that are deconflicted and assigned to groups of vehicles. So we have a formal definition for a geofence that defines the polygon, the ceiling and the floor, and also defines where it is in time and space. So that allows this polygon to move. And it allows it to have a start time and a stop time. Right? We make it have non-self-intersecting boundaries, because if the boundaries intersect, then it's not one polygon. And this is showing the notion of both a durational and a trajectile geofence. The blue geofence is static. It's there all the time. The green one is durational. It has a start time and a stop time, but it doesn't move. The teal one has both a start time and a stop time, and it moves. So these are the three different types of geofences that you could define. And you want to be able to handle all of them. Well, in most of the work that we've done so far, we've looked at both static and durational geofences. We haven't finished our analysis with trajectile geofences because they're much harder to deal with. But we could make them durational geofences. That's kind of a weak argument. So this is an example of how you want to deconflict them. In this case, we had a triangle that was blue, static geofence there all the time. And then we have the green geofence that was requested by a new aircraft. Well, the altitudes are different. So to maximize airspace utilization, we made two altitude bands. One gave the green UAS everything they wanted between altitudes 5 and 10. And the other band required the new geofence to avoid the blue. So you can keep going with that. The blue, kind of teal light blue one was requested after the green one. So as long as you can do basically set difference operations with polygons, you can make these airspace regions not conflict with each other. This is an example of a static set of geofences. When you put time in, then you end up with something similar. In this case, the blue one had priority, the green one had the next priority, and the yellow one was last. Both the blue and the green and the yellow are durational geofences, so they have different start and stop times. What this shows is that as long as the vehicles and the central UTM agent is able to understand what these boundaries are over time, you can think of this as fast forwarded over hours, not seconds, because it would be ridiculous to have a geofence for a few seconds, right? So this is vastly sped up from what it would really be. Then you can actually use knowledge of this, which would be negotiated before the flights ever begin, to build flight plans. So now let's look at that. Suppose your vehicle has to stay in the yellow and it's flying right to left. Well, you saw it speed across the green so that it wouldn't be in the way, and then it kind of hung out more slowly after it got past the green as it's waiting for the blue to go away. So this is the type of interaction between the path planner, which would be on board a UAS, and UTM, which would be telling the UAS what its geofenced boundaries were over time. So another thing, now going to the vehicle perspective, you want to make sure you don't actually leave or leave a keep-in boundary where you're supposed to stay inside, or enter a keep-out boundary, like over the Statue of Liberty. And so you actually need the flight controller to be warned before you actually get to that boundary about the impending boundary. So that requires layering the geofences. So in this example, on the left, the black is the no-cross keep-in boundary. The blue is an override layer, which says if your UAS crosses that line, any of the line, it's going to have a geofence override controller that takes over. If it's a multi-copter, you slow it down before it gets to the black boundary. If it's a fixed-wing aircraft, you turn it back because it can't actually slow down and stop. And then it won't cross the black boundary. The green is a warning layer. If you have a human in the loop, it says, hey, you're getting close to where it's going to override, so it's not a complete surprise when the guidance system turns it on. The one on the right is, the one on the left is very easy, right? That's just rectangles. It gets to be a little harder when you have arbitrary concave polygons because you can easily have irregular shapes that cause the layers to basically overlap each other, invade most of the region, and so on. So there's work in two directions here. One is handling the arbitrary concave nature of the polygons. The other is understanding what those layer distances need to be. So this is showing the two components of the buffering for layers. One is a uniform buffer, which represents the deceleration or the turn back distance needed. The other is a directional buffer, which allows you to take steady wind and basically blow out your layer so that you're not going to cross the hard geofence boundary, even when you have wind blowing you in that direction. So you can do this for hover-capable vehicles. This is just looking at a really, really simple model of deceleration. Oh, and this graphic is kind of bad. It's supposed to have a full 180-degree turn. This is looking at a vehicle that would have a minimum turning radius. We'll go past that. So you generate the layer distances. The vehicles then know when to execute an override turn-back maneuver. But before they do that, they need to know where they are. So another branch of research in this was looking at arbitrarily convex or concave polygons with an arbitrary number of sides. Normally the way to do this is a method called raycasting, where you basically look at the intersection distance to every edge in a polygon, and you can do that relatively quickly, but it is linear in the number of edges of the polygon. This algorithm, which uses a triangulation to create a set of triangles that map both the interior of, say, the keep-in geofence polygon, as well as the exterior region, because you have to also know if you've crossed the geofence boundary into this exterior, so the red is a bounding box. You can create a graph. It's an adjacency graph that describes where you are. And with this adjacency graph, given that you're really checking your position every control loop, which could happen at 1/100th of a second or so, you're not going to have moved many triangles. In fact, in almost all cases, you're going to have moved 0 or 1 triangle, which means that if you run this at a high speed, your computational overhead is constant. It's order 1 complexity for those that look at computational complexity. So with this type of algorithm, combined with the layering, you can run this on board in real time with arbitrarily complex concave boundaries of geofences and be guaranteed to notice when you cross the warning or override layers in time to turn back. So this is an example of putting them together, the layers, the triangulation, and then here's an example, and these are not cooperative. This is 2 different simulations put on the same plot of where 2 quadrotors are being commanded by a bad pilot or bad software to fly outside the geofenced boundary. So you can see in both cases, they don't do anything at the warning. When they get to the blue override boundary, they turn back. Now in this case, this is local loiter. This guidance mode turns them back to the warning boundary closest to where they exited the override. Another guidance strategy might be return to launch. Now this example was chosen carefully because if they go in a straight line, they're going to violate the geofence boundary. If you look at most of the manufacturers that have geofencing built into the unmanned aircraft, such as DJI, which is the major manufacturer right now, when they do return to launch, they assume a straight line is sufficient. Right, so that's not quite good enough. And in fact, there are some really funny YouTube videos that show their vehicles flying into buildings because they have no map and they have no sensors. They just know they need to fly in a straight line. So not that that was a good thing to do, never fly your drone into a building on purpose, but it was an interesting illustration to show how we need better technology than what is being delivered right now. So this is showing how if you follow, say, the warning boundary, that you're going to be a safe distance away from the edge of the geofence, and it's a quadcopter, so it can maneuver there safely. So before I go on, let me ask if there are any questions. I know that's kind of fast, right? This is my rendition of an entire PhD thesis that was completed about a month ago. Comments? So I'll tell you, the main comment I hear from NASA, FAA, and people who are used to the kind of tube around an aircraft separation assurance models that are used is that this will never catch on, because we're so used to thinking of traffic locations on a radar screen that we'll never get to a point where we want to cut up the airspace like this. So if you look at anything flying above a few hundred feet, and you assume that they're flying point to point, like with a commercial transport aircraft, they're right. But a lot of the envisioned missions for unmanned aircraft don't do that. Whether you're inspecting a structure, delivering pesticide to a farm field, doing search and rescue, there are so many different applications. I could go on and on. These vehicles don't have trajectories that go point to point. They are responsive to the sensor data that they're collecting in real time. There have been a lot of proposals for vehicles to work together, and they're doing complex accelerated trajectories. So the most direct analogy from this geofencing to what we have today is the aerobatics box, which has existed for a long time in general aviation. So the aerobatics box is an airspace, literally a box of airspace, that can either be active or inactive. If you're a general aviation pilot and you want to do maneuvers, or let's say you want to have a good time with loops and rolls and spins and all kinds of stuff you see at air shows, while you're doing those maneuvers, you can't look for other traffic because you're busy looping or spinning and you can't see them. So for many, many years, well before I learned to fly, they've had this thing called an aerobatics box. If you take your pits out on a Saturday and you launch and you go and you want to do these maneuvers, then you call out on the air traffic control frequency that goes with that airspace, hey, the aerobatics box is active, I'm there. And then you freely maneuver and you trust that all of the other vehicles are going to avoid that box because you can't see them, right? So that's already done. This is only extension of that, which is scalable with proper use of math. Okay, yes?
Would you think that it will be a better transition first to use the box concept around the current systems so the resistance will be least because they're used to it for so many years now, 70, 80 years. So then transition them into the current the models that you're suggesting here. Would that make sense?
Well, so that's what people are trying to do right now with things like power line inspection. So I've, railroads, so there's a railroad that has beyond line of sight authority, and they basically put boxes around their tracks. The power lines put boxes around their power lines to inspect. So that's been used on a case-by-case basis now. There's two reasons not to go that direction. If you look at what's done now, they assume they're the only ones there. They reserve giant boxes over, say, 10, 20 kilometers of railroad track or power line, and they just keep it all day. Nobody cares because they're the only ones flying there right now. If you imagine a future where there are thousands of unmanned aircraft flying in a shared airspace over a short period of time, if the railroad company or the power company has a monopoly on that airspace for a long period of time, nobody else can fly there. The reality is, a lot of the places that people fly will be influenced by the shape of land, whether it's land use type, like water versus city buildings, or where the traffic is, traffic patterns going in and out of an airport. These things are not guaranteed to be boxes. So if you go down a path where you start with boxes, you're going to establish, and this scares me to say it, I'm feeling fear right now, precedent and legacy in the FAA. And once legacy is established, it is very hard to roll back. So if you don't get it right, from the first time this transition is made. It could be decades before it's changed, and we would lose a lot of the flexibility in using airspace.
Would we be not utilizing the path, for example, going from here to point A to point B by road? It's not necessary that only my car is going. We have multiple lanes of cars.
Absolutely.
We're following one behind the other, and with an automatic braking system, in a way, we are creating a space for each car so they're not bumping into each other. Would that be another way to consider these planes going in one path, but one behind the other without hitting each other, so you can multiply the productivity of the whole operation?
Absolutely. And what I would say for that is you would form a geofence around your road lanes, and you would allow into the north direction geofence the traffic that could follow each other and obey the rules of that road going north. And you would put into the southbound geofence the vehicles that could obey the rules of the road and were flying south. They have to have consistent speed constraints, right? Just like on approach and departure. So once you box those out and you have traffic flowing all the time, there's everybody else. This would support that. It would also support the adjacent farm field that needed pesticide to be applied that day, or the city park that allowed model aircraft. So there's all kinds of reasons to like this geofencing, even with this notion of traffic flow, because you need all this other support for activities, not only the high-speed traffic that's going to be going a long distance on the freeway. Having only support for that traffic would be like being here in Miami, keeping the freeways and taking away all the side streets. It doesn't work very well. So we can go that direction, but if we do, we're really restricting the set of operations that we're going to allow, especially in urban areas. Yes?
I want to make sure that I have understood. So what you are implying here is that there is in fact no preliminary planning of the airspace that is going to be used. It's more of a reactive, as we are using the airspace, the evolution of the system works according to that. In other words, you need to do a flight plan to go from point A to point B at 1400 and taking off right now, and I have some sort of a priority or not even necessarily the airspace freeze according to my needs.
Yes. So the proposal here is that well before you fly, you ask for an airspace reservation, right? It could be that you're going to operate on one of these roads.
So you do make a flight plan?
Yes, absolutely. Right, but you don't have to make a flight plan if you're not sharing the airspace with anyone else. So if you're entering the road geofence, which would be one of the many highways that the traffic that's flying point to point would follow, then yes, you just have to make sure you're one of the vehicles that's been approved to fly. It would look very much like IFR now. If you're not flying on one of those roads, then you reserve an airspace boundary, and then you either have exclusive access or any vehicle that had compatible systems for detect and avoid would have common access to that boundary.
So let's say that I am planning to make a power line inspections at 1400, and it happens that there is a huge thunderstorm in that area.
Yeah.
How do you evolve there? How does the model react to that change in the conditions?
Yeah, so that's what this example is. The yellow butter stick is the power line inspection. So in this case, let's say that there is some kind of obstacle, or there's another use. I don't know what these are. Maybe they're a farmer that wants to go out and look for animals. Whatever it is that you want to imagine there, that have different geofences that have been put in place, right? Usually when you have something like a power line, you have dual use of that land. There's something going on near or under that power line as well as that power line. If the power line company takes that airspace all day, which they typically would if they're operating there, then nobody else can fly. So the butter stick would get that entire day. So what this is saying is, let's say somebody wants to go out and count their animals. Let's say they want to apply pesticide, many other uses. Then they can negotiate the airspace with the power company to make sure that those very diverse operations are all supported and that they won't hit each other, because this is not hard for a computer. It's very hard for a human air traffic controller, not for a computer.
But so if I am Amazon, I can block the entire space about Miami and then say it's my space, okay, for delivering
So I assure you that I am no fan of Amazon, right? I own my backyard's airspace up to the immediate reaches boundary of probably a couple 100 feet. And I do not want my neighbor's shoes passing through my backyard on the way to theirs. This actually enables control in that sense, because my land has a boundary that's known to the city land maps. And if I want, with this structure, regardless of how odd-shaped my land boundary is, I can go and say, just like with white pages, I don't want my airspace listed on the map. And I like to think, as we go forward, and we have these debates of who owns the airspace right above the ground, that we come up with a solution that allows communities to have input as to where in their community they want the drones to be flying versus where they shouldn't. This is an enabler of that. Now, grad students are not in a position to make legal decisions. So the best that we can do in aerospace engineering is to provide technical solutions that can support UTM by saying, this is real-time, computationally tractable, provably correct algorithms, I guess it's plural algorithms, that you can put both on the UTM side to deconflict the airspace, and that you can also put on board and use in real time. So if we actually get to this point, then we can use the airspace connected to the land for any purpose we want. It is not my job to say how they negotiate that airspace. Personally, I would like to see the farm field between Amazon's warehouse and the city that had corn, you know, that Cyber Monday nice little video that Bezos showed. I would like to see that farmer get some compensation for Amazon flying over their space, right? But right now, we run the risk of having new companies get all of the money for sharing maps where the landowners get nothing, because we're not even looking at a public entity keeping those maps, right? And we also risk having the powerful voices that say, open the airspace to all of our commercial purposes, not have any responsibility for figuring out what to do with different land uses. And they'll say things like, well, it's too complicated to do things with these strange-shaped land, or the strange-shaped bodies of water. And the whole idea here is that it's not. We know how to deal with geometry, right? It's not that hard. Anyway, I'm probably using up the whole time. How much time do I have? How much longer do you want to stay? You're in charge, right? Who's in charge? Okay, let me keep going, but then if you need to leave, please do. Okay, so contingency planning. How do you deal with that? Well, first of all, we start with where we are now, right? We know how to do a lot of things autonomously on aircraft, things like flight planning, guidance, navigation, control, sharing information. And then we ask the question, what can we do better? Well, right now, if you look at the status quo for commercial transport aircraft, what we do is we take autopilots and we turn them off when things go wrong. Well, maybe that's not the best if you want a fully autonomous aircraft and you don't want them to crash. And interestingly enough, there's been a push in the small drone industry to just put a parachute on board. So like recently, a company called Matternet partnered with UPS, and they've actually been approved to fly medical delivery in North Carolina. And their solution, if something goes wrong, is to pop a parachute. Well, I have some problems with that. Imagine that you're driving down the road and a drone lands on your windshield. Doesn't hurt you, right? Because it has its parachute going, and so it's not going to necessarily crack your windshield. But you may crash anyway because you can't see anything because there's a parachute on your windshield. Well, now imagine you're in Central Park pushing your baby stroller, and you've put the cover back because you know, it's a sunny day, it's nice outside, not December in New York, which is unpleasant. Maybe it's Miami in December and you're doing it instead here. Well, same Matternet drone popping its parachute, carrying a blood sample that may or may not have a disease in it, lands on your toddler. Right? It doesn't matter that it didn't kill them with fast spinning blades or mass that will, decapitate you or punch a hole in your face. Right? What matters is that you were peacefully going along and a vehicle fell from the sky and hit you or your kid. Neither of these are good solutions. So what you need instead is an ability to have the resilience, the redundancy, and the intelligence, whatever that means, to not have these vehicles fall from the sky and hit you or your car or your kids or your dogs, and the list goes on. So that's what we're looking at. How can we take new data sources, incorporate them into real-time decisions, and use them both in nominal and emergency flight planning so that those terrible things don't happen. This is work that my group did, 18 years ago, that was largely ignored because the community was like, commercial transport need to never make emergency landings, right? They're so reliable that there's no problem. We don't need them. Most of the time that's true, not all the time. Nonetheless, this is what we did, and it was inspired a little bit by the space shuttle. So the space shuttle, everybody is pretty obsessive over it actually landing safely and the astronauts getting out alive and the vehicle being okay. So whenever it comes into the atmosphere, there's a lot of violence that happens with heating and so forth, and then it gets down to lower altitude. All the time there's this thing called a footprint calculation. Where can it go? If something happens, where are the places on the surface of the Earth that it can go? And so we adopted that as well and put that in the first step. If something goes wrong with your airplane, where can it go? Draw the circle or whatever on the ground, and then pick landing sites that are within that circle. It doesn't make sense to look at anything else. Rank them, choose one, build a trajectory and land there. Oddly enough, that sounds simple, right? It actually is pretty simple. As an academic, as a junior professor, I will tell you, the worst curse in the world is to do something that makes sense, but that is so simple that nobody wants to acknowledge that it's there. Right? I faced that. Everybody was like, that's not research. And I'm like, so what is research? If you have a practical solution that solves a problem, this should be good. So anyway, obviously I survived and have moved on. But this flowchart, which was originally for manned aircraft landing on runways, still applies today. This is kind of the killer app for that particular thing. So that flowchart was from 2001. This is from 2009. This is the Sully Hudson River case study. I assume I don't need to say a lot about that. This is the black box data. One of the things you should do in your spare time if you care about aviation accidents is go to the web and type NTSB accident dockets. There you will find links to all of the data from all modern accidents that had black boxes recording the data. You can download them as a CSV, comma-separated variable file, and open them in Excel or MATLAB or whatever your favorite processing tool is. And voila, MATLAB. 5 minutes later, you get the black box trajectory of US Airways Flight 1549. So I'm not claiming this is great research achievements, but what this does is set the context for what happened. So you see LaGuardia, plane climbs out, everything is normal. You initially have a steep climb, then you have a cruise climb, which is not quite as steep. Birds hit right before the top. Black square is kind of where you had enough seconds for autonomy or the pilot to say, I don't have engines anymore, I'm gonna have to come down with no engines. So that's where we started our flight planner. Right, the rest of the trajectory is solely basically coming down and landing in the Hudson River. At least one of those blips was the George Washington Bridge, and the pilot was like, I mustn't hit the bridge, and so they, reacted by pulling over the bridge. Well, this is the flight planner from 2004, I guess, with the approximate glide characteristics and turn characteristics of the A320 that was being flown. And what you find here is that if you immediately, within 4 seconds of that black square, run the flight plan, the emergency flight plan that's calculated in under a second, because this is really simple. This is something called a Dubbin's path, which is turn, fly, turn. It works for any fixed wing airplane. You put in a glide slope. What we choose in our work is halfway between best glide and steepest glide as a nominal choice, because that makes sense. Right? That means that you have margin. If the winds are different, your performance is a little different than you expected, you can build a path in a millisecond or under on a reasonable computer, because it's a simple iteration guaranteed to converge. And what you find in 4 seconds is that you can land into the wind, which is extremely desirable when you don't have thrust reversers, right? Because this is all brake, friction, stopping. If he waited 8 seconds or more, he lost that, because to land on the same runway, you have to go past and come back and land. So the paths were shorter to do the crosswind runway or the kind of upwind runway, which means you're kind of, or downwind, meaning that you're being blown toward the runway, so it would be a little harder to stop. After 16 seconds, you can't reach any of LaGuardia's runways. Right, so there were two problems which made landing in the Hudson River the right choice. One, he didn't have this on board. And as far as I know, commercial aircraft still don't have these simple planners on board. Right, and you can hear in the cockpit voice recorder him saying, I can't be sure that I'm going to get back. Right, because no human can pull out their flight materials and their calculators and make sure that these types of things will work in under 15 seconds without the computer saying, boom, here's your trajectory, here's your margin. The other thing is we have voice-based air traffic control. It took 15 seconds for him to get the people on the other end of the line, the air traffic controllers, to recognize that he was a jet with no engines. Right? He said in calm terms, I have a bird strike, right? So what I learned from this is if I'm flying and I have an emergency, whether I'm panicked or not, I sound panicked. Right? Because you get a very different response at the other end of the voice. If you're like, 1549, we've had bird strikes, we've lost both engines, right? Which is roughly what he sounded like, right? Which to his credit meant that he was calm and thinking clearly. But on the other hand, air traffic control was like, oh, you know, cool, calm, collected pilot is telling me, what? Oh, bird strike. Oh, 2 bird strikes? Notice how much time passed. Right, so by the time they started vectoring other traffic away, it was already too late to get to any of the runways. So what are the solutions besides yelling, whether you're panicked or not, so that air traffic control is like, get these people out of his way, right? He's going wherever it is that he wants to go because he's lost his mind and is panicked, right? That's what I want there, right? You want the human response to be fast, and that's how you get it. Well, better than yelling into a radio is having a data link, right? Right now, air traffic control says no data link should be used for safety critical instructions besides detect and avoid traffic information because we need to hear the inflection of the voice. Maybe the data link would have cybersecurity issues and so on. We have a choice. We can have high-speed data transfer which is precise and fast. Or we can continue to hold on to the notion that voice is the way we should communicate. You know where I'm leaning here. Also, if you go to data link, by the way, you get to support all these autonomous operations, whereas right now, for unmanned aircraft, there is someone sitting at a ground station with a radio that talks to air traffic control. How inefficient is that? Right? You basically have somebody sitting there to translate between the unmanned aircraft, which has no ability to directly interface to the air traffic controller by voice, and the actual air traffic controller, which slows things down even more. The person at the ground, beyond line of sight, has no situational awareness of that UAV beyond what the data link has already sent them. So if that data link was spoofed, it's already been spoofed. All right, those are the lessons we learn. Go to data link, have your emergency flight planner, it'll help. So what are we doing? Well, basically there's 2 things you can put together to obsessively study this emergency flight planning and landing problem. One is you carry onboard sensors, you look with them and you say, where can I land? So this has roots in the helicopter community, military helicopters being in areas where you may or may not have a prepared landing site. If you need to come down, you need to land, let's say you're rescuing someone, then you use your sensors, radar, LiDAR, video, whatever you're carrying, to determine a clear area and go there. That's the sensor-based planning path. The other path is using maps. Right now, we've planned flights with commercial transport exclusively using maps. Things like where are the tall towers, where are the mountains, what altitude are the runways, what are their orientation, length, width, all of that stuff on maps. Well, if you have to do an emergency landing because of some failure or hazard in the environment, you want those maps to be as expressive as possible. Our maps are very old in aviation. They were aimed at human pilots having simple enough abstractions of what's really in the environment to look at things like runways and little peaks of mountains which represent antennas and terrain. Well, we now can do better. So if you're in an emergency, you look around with your sensors and there is a safe landing place, do it, land, don't stay up in the air. If there is no such safe place in the nearby environment, which will happen frequently in urban areas or complex terrain, don't just give up anyway or fly in a random direction. use maps. So what might those maps look like? Well, this is showing how we can take raw data, like LiDAR data, geographic information system data, which includes satellite imagery as well as LiDAR. OSM is OpenStreetMaps. It's a totally open database of roads, waterways, land use, overpasses, power lines, many other things that's classified, that has GPS coordinates. Census and cell phone data determine where the people are. Census at night, cell during the day. And terrain maps. We can also take city building maps, like the Pluto database for New York. And then we can process all that information to get building, landing site, population density, and terrain analysis to go into two purposes. One is building a landing site database that doesn't just include runways. And two, building a risk map, which looks like a heat map of the environment, so that as you're building your plan, you can fly over low-risk areas. So this is an example of using OpenStreetMaps to find straight road segments for fixed-wing aircraft experiencing emergencies. So if you look at the bottom right, that's really the important one. What's happened there, the little triangle in the middle of the circle is an aircraft that's experienced, say, loss of thrust or fuel starvation, so it has no engine. And the dashed line is the footprint. Go back to that yellow, strange-looking flow chart. The asymmetric segments are roadways that are straight and have no obstructions over them, coming from that database of roads. And they're asymmetric because you want to land in the same direction as traffic. Right? So we didn't have this, but an obvious next step is to take something like Google traffic data and put it in. And then you turn your straight road segment into a place that a plane can enter, like an entrance ramp on a freeway. Right? Now you're going to snarl traffic, right? Because you eventually are going to stop your airplane. You're not just going to cruise down the highway. You have no engine. You're going to stop. That's a desirable thing. But then you don't have the type of risk that you would have of being in a place where you are out of distance of a reachable runway. So that's one example for fixed wing. This is an example of using call detail report data from cell phones to fly over areas of low human occupancy. So this is a paper. There's actually a follow-on in a journal. If you look on the left, you see 6 a.m. in Milan, Italy. Why are we in Italy? Well, the reason we're in Italy is because there was open data sets for call detail reports for a period of 2 months, and that's so hard to get that we grabbed it. On the left, you see that there aren't many people downtown. So the planner chooses to minimize risk during the flight to land by flying through low populated areas of the city. On the right, you see it's 9 a.m. People have arrived at work. They're using their cell phones. So you can see that the emergency flight plan tries to get out of the city as fast as possible. Obviously, the one on the right has higher risk than the one on the left based on flying over unoccupied areas. So now the final thing I want to talk about, which is kind of attractive from the modern day, we want to use machine learning for a lot of cool purposes. So far, nothing that I have said uses machine learning. So now I'm going to transition to one of the most recent things that we've done that does. And this is learning roof shapes for small UAS emergency landing. If you're flying in an urban area, again, you don't want to land on the people, you don't want to land on the cars. So going to streets and sidewalks and parks and all of those places on the ground, actually in an urban area has quite a lot of risk, especially somewhere like here where the weather is always nice and people want to get out. Well, so much lower risk is to go to a flat rooftop that tends to not be occupied. Now, you could say, what about that party on my roof? Well, the likelihood of you having a party on your roof is much lower than having some pedestrians on the street. So we're going to start there. Well, so what we did then is we downloaded from the USGS, the geographical system people, LiDAR and satellite data, and then from the city databases, building outlines, also from OpenStreetMaps. We processed it together in a multi-stage convolutional neural network, random forest classifier system to give us roof shape, geometry, and location. Here are some of the roof shapes. that we tried to classify and what the RGB imagery and the LiDAR data looks like. To you, probably the RGB imagery is a lot more revealing, but to a machine learning system, actually the LiDAR is better because it's giving you depth, right? Whereas RGB, you have to kind of correlate colors with slopes, which is harder. So we started in Witten, Germany. Again, going to a random place in the world, and the reason we went to Witten, Germany, you've got to love what students can find, right, is that the student found that there was this guy in Witten, Germany, I don't know if it was male or female student, or professional, or somebody with nothing better to do, that had pre-classified the shapes of all of the roofs in that city in OpenStreetMaps. Score, supervised machine learning, done. So we're in Witten, Germany. Right, obviously he didn't just trust all of it, he double checked here and there, but it helped reduce the amount of overhead. So we took the data from that city, RGB, LiDAR. It also turns out that Europe has pretty high resolution LiDAR imagery, so that was good too. And combined, and the accuracy of the machine learning system was above 95% for either LiDAR or combined, and the combined improved a little more. That's pretty good. So the conclusions were if you have clean data, you get excellent results. And combining modalities, meaning RGB and LiDAR data, is good. And then truth hits. So human, this is my grad student, Jeremy Castano, had to manually remove images. This is him complaining in this slide. I love this slide, so I present it also because this is the plight of a grad student who studies machine learning. Right, so he had to manually remove images from Witten, Germany. He also didn't want to require a human to say this is bad data, don't make a prediction. And so then he also went to other cities and said, okay, we have to create a new category called unknown. So this is actually a pretty powerful tool in any machine learning situation, is to allow there to be a place, a bin, to put all of the imagery in that you actually can't classify very well. And as long as you train the imagery to be that class, then you have improvements, right? So the unknown class was things like bad images, overhanging trees, things like that. So then we went to Manhattan, and he disappeared for about 2 months because Manhattan's rooftop geometries are quite different than Witten, Germany's. In Manhattan, most of the rooftops are flat, but they have things like water towers, air conditioners, exits, many other things, just part of the infrastructure. Since there are no yards, you have to put everything that would normally be in your backyard on your roof. So we created then a new category called complex flat, which means that it's flat underneath, but it has a lot of things on top of it. So then we trained the same network on a mixture of Manhattan and Witten, Germany data, and then we applied it to Ann Arbor, Michigan. Well, I'm in Ann Arbor, so that explains that, and so was Jeremy, so that's why we did that. And what we found was that even though we went to a new city and had no training data, that we were able to get above 85% accuracy with that network. So that's a pretty promising result because that says that we don't have to pay a whole army of grad students to go to every community in the world and separately train the data, that as long as you've trained with the architectural types that you can expect to find in new cities, you can go to those places and find them. So then the next step, but this is showing the results are only 86, 87%. They're not in the 90s because we're training on a different city. So then the next step, because in a place like Manhattan, everything is a complex flat roof, is to find the flat sections on the complex flat roofs. So this is using a method that again focuses on using computational geometry to allow the translation of point cloud data for that rooftop to maximally sized flat areas that have no holes and no obstructions. So this is a technique that we've called poly-LiDAR. We have a paper that's in the second review pass, hopefully will be published soon, that describes this algorithm, its complexity, and we're pretty excited because I think it's faster than what's been published before. So with this then, with the first stage, we can find the complex flat roofs, and with the second stage, we can find and size the maximum clear flat landing area, and each of these can be used as a landing site for a quadrotor type of vehicle. Anything that is light enough to not break through a roof and that is capable of maneuvering to land vertically and take off vertically. All right, so this is the final slide that I'll show. When we're done, we have a map of possible landing sites, and we have a map showing the risk of flying over each area, which can be integrated to give us an integrated risk over an entire landing flight path. There's a trade-off, and there's no way to escape that trade-off. So let me go back to the Sully case because it really illustrates what this trade-off is. In the case of the US Airways flight, landing on the Hudson River had extremely high risk of the landing site because it's, commercial transport airplane landing on water, high risk. But the path risk was very low because that plane spent almost its entire time flying over water, which posed very little risk to people on the ground. If the plane had gone back to LaGuardia, the landing site risk would have been extremely low. But the path risk would have been very high because here was an airplane that was damaged. It knew it didn't have any engines left, no thrust. The engines were still on the plane, but maybe they weren't secure even. Flying over a whole bunch of houses and apartment buildings and businesses, going back to LaGuardia, right? This is a trade-off that is very difficult for an engineer to make without a discussion among people in the community, right? When you have an emergency and you're flying over a populated area, do you place risk on the people on the ground and go to the safest landing site? Or do you risk the people on board and stay away from the populated areas? That question hasn't been answered. And so the best we can do then is to quantify the metrics and the trade-offs to make. And this is showing a Pareto front for a random example in Witten, Germany of a UAS needing to land. And usually what you find is that you have a whole bunch of solutions that are dominated, meaning that they neither have the lowest path risk or landing site risk, and a few that are on this front. Ideally, you want to find one that minimizes both at the same time. But if you find something like this, then ultimately, whether it's humans or autonomy, you're going to want to point and click and say, I want that one. My belief is that if Sully had had this in real time, with pictures of what those plans looked like, that would have been the best possible case of having a human in the loop, because he could have decided right then and there whether he wanted to fly over the populated area to get to LaGuardia or whether he wanted to just put risk to his people on the airplane and fly to the Hudson River. But he didn't have this, so he did the best he could. That's it. Thank you. And thank you for putting up with me for so long. If you need to leave, please do. Happy to answer questions.
Another question. Do we have the artificial intelligence capability to, in fact, make those decisions rather than emotional decisions from a pilot?
Well, so I guess I would claim that that's not artificial intelligence, except in the processing of data related to landing sites and making risk maps. That's the only AI here. Ultimately, if you use autonomy for this, then there's going to have to either be weights in a multi-objective cost function that someone has decided in advance, in which case you don't have a Pareto front, you just have predetermined weights, or you have to give some criteria to that particular plane. And then you get into discussions of the trolley problem, which are common in AI. So the trolley problem is as follows, and this is a very classic discussion of self-driving cars. So suppose that you're driving along or you're in a trolley and you have a choice between hitting a pedestrian or hurting or killing someone on board. Which do you do? Well, that's a classic problem. Now, if you look at the self-driving car community, what they will say is that's not a useful discussion because you have to do something no matter what situation you're in. So the best you can do is to do something like this, to create metrics, to quantify what the risks are, and then to find an overall best solution, right? So I guess I would have said here, if you look at the margins, that plane was better off flying back to LaGuardia than it was landing in the Hudson River, because the landing risk would have been near the very top. Landing in the river is such a bad choice for an airplane, right? And flying back to LaGuardia when your engines have failed, but the plane otherwise seems to be handling okay, actually is not all that dangerous. So even though there has been discussion of, wow, what about flying over all those houses between where the airplane failed and LaGuardia, if you actually do the quantification in a fair, objective way, what you find is that the likelihood of anyone being injured because that airplane flew over those houses as a glider was actually very small, because we know how gliders fly. And if there had been a flight control problem, it would have been impossible to keep that airplane from drifting over Manhattan, which would have been worse than flying back to LaGuardia anyway.
I mean, this is wonderful. I'm very inspired to hear all of this. But in terms of the data for your assumptions, you didn't flash any screen with data.
Oh, I needed to state my assumptions, didn't I?
To create the basis why you think that this is even a problem to resolve. Is there an overwhelming evidence, in your opinion, research-wise, that this is going to be a real problem in the next 5 to 10 years?
Yeah, so if you look at commercial transport aircraft, no. That's why the early stuff never was picked up and used, because in commercial airplanes you have triple redundancy and you usually have 30,000 plus feet of altitude drop before you actually hit anything. Right, those two put together give you a huge, huge advantage safety-wise. But now we're talking about singly redundant drones flying less than 400 feet over populated areas. So all of those things that give you safety in commercial transport, namely the altitude cushion and the triple redundancy, are no longer there. The human reaction time is so slow, it's on the order of a second or two when there's really an unexpected situation that they encounter, even if they're very good, and they're not on the airplane, they're sitting somewhere looking at a control station, that 400 feet of altitude will be lost before they even notice what happened. So that really means that the autonomy has to recover the vehicle before the pilot would be able to even intervene.
Can there not be the box concept for even the drones as well as a initial point of thinking?
The box concept meaning keep them away from populated areas?
I mean, have a airspace around each one, although it won't be as large as for the commercial planes.
Yeah.
This will be concomitant with the size and the range and the speed of each of these.
Yeah, so one thing that I always assume is that the plane that's doing emergency flight planning is the only one in the sky. And the reason I claim that's a good assumption is because if you truly have an emergency and you declare it over your data link immediately, then you don't have to detect and avoid other traffic. That's the way aviation works. And the reason for that is that you have an emergency. And so you need to prioritize your aircraft doing what it needs to do to land safely. And everybody else that doesn't have an emergency can turn away. So that means that you don't need the bubble around that airplane, except from the other vehicles' perspectives. So yes, I totally agree with you that once you have an emergency airplane, you put a bubble around it, but then it doesn't care about that bubble, everybody else does. So then you go back to the geofencing discussion. In terms of flying, the reason I use Manhattan a lot, and you could use Miami a lot as well, especially if there are pizzas being delivered across from somewhere to the west over the freeways and buildings to the beach, is that it doesn't make sense to fly over strictly unpopulated areas if you're doing a lot of the missions that we envision for drones in urban areas. So there is no such box that can protect you from flying over people.
We have a lot of Everglades, fortunately.
So maybe you're okay, but certainly looking at cases like Manhattan, you can't do that.
Yeah, at least my last comment is this, and this is from an engineer to engineer, and all of us. We as engineers, we find a problem and we solve it. But we always seem to create more problems for the solution that we have created than actual solutions. Mm-hmm. So the best way to me, it seems like we should do a major scenario analysis, looking at every possible thing that can go wrong. For example, you raise the human factor situation, which is very realistic. I don't think when we hear about autonomous vehicles, this has ever been even talked about. Even though it's a small little cabin, two people can, husband and wife can fight with each other and can go, something can happen. So the point I'm trying to make is, how much of that scenario analysis, not necessarily by you and your researchers, but in general in the aerospace academy, have they done that so that we are at least aware of a plethora of all possible scenarios, so that when we try to develop a solution, it will minimize the maximum risk. We can never eliminate the risk as an engineer when we solve a problem, but at least we can minimize it.
Yeah, so in aerospace engineering departments, as you guys well know, we tend to have structures and materials, gas dynamics, and dynamics control groups. Each of those groups tries to minimize the risks with respect to their own lens, right? It is much more rare in aerospace engineering departments to have people who look at the full system and minimize those risks. For that, I think you would look outside aerospace engineering for the most part to people who study systems engineering. And whether it's industrial and operations or some other branch of engineering, those are the people that are doing this type of analysis, not aerospace. So my group, as much as I like to do that type of analysis, we can't focus on that because our students don't get PhDs for that purpose. Their classwork and their interests don't match well with doing systems analysis of that sort. So I think people are doing it. I don't know, I think if you look at the large companies that have been delivering vehicles for a long time, they've been doing that for a long time. If you look at the emergent companies, the ones that have deep pockets, I think they're doing it. The ones that have shallow pockets, they kind of scare me a little bit. So we'll see.
It's very interesting research, what you're doing.
Thank you.
Yeah,
Thank you.
very much.
Well, I think, let's cut it off here. I think Dr. Atkins might stick around and maybe have a cookie or something. And on behalf of the University of Miami College of Engineering, we have a little gift that.
Thank you.
Thank you very much. That was fascinating.
Thank you.